In this video, we will discuss the solution to problem D cases from Codeforces round 961. Now, before you skip this video after seeing fancy terms like SOS DP, let me preface by saying that this video is divided into 6 different sections. So, if you are a beginner to Bitmask, the first 2 sections might be interesting to you. If you are familiar with submasks, the next section might be interesting to you. If you are familiar with tree DP, the next 2 sections will be interesting to you. And if you have good enough experience with bitmasking DP, the last section will be interesting to you. In this video, we will talk about what SOS DP is and what is the main principle that makes it work. Since we have sections covering different time complexities, I have created easy version of this problem in my Codeforces group, the link of which you can find in the comment section below. This is the problem statement. You are given a string and you need to split it into multiple parts where the size of each part is less than or equal to k and the number of unique characters of each of these parts is minimized. So this is a short summary of the problem where you need to split this string into multiple parts and the size of each part should be less than or equal to k and the number of unique ending characters of each part should be minimum possible. Now, after seeing this problem, you immediately come to the conclusion that greedy approach might not work. That is, if you are given k is equal to 4 and you try to greedily split to the longest possible size. So this is the first split, this is the second split, third split, and the last split has to end at the last character. So you see that the number of unique characters is 4. But if you had done this split smartly, it was possible that all of these empty boxes contained D. So the number of unique characters could have been minimized to just 1 instead of 4. So since this greedy approach does not work, you might think that greedy is not at all applicable in this problem. And if you remember, we encountered this same situation in our previous video where we were discussing a tree DP where a greedy was immediately obvious that it is incorrect. But there we talked about one important aspect, that is, even if a greedy is incorrect, you should try to explore other kind of greedy ideas, because even if they are incorrect, they will give you some insights to the problem and they will actually help you optimize the DP approach if one is even needed. Now, let us talk about a non-obvious greedy solution that is indeed correct. Suppose I give you the optimal answer and I tell you that in the optimal answer, the colored boxes represents the letters that are present in the optimal answer. Also, let us call each of these colored box as a checkpoint. Given this information, can you figure out a strategy to split this string into several parts such that each part has size less than or equal to k? Now you can see that if you are thinking of this problem backwards, that is, if you are assuming that the answer is always given to you, in that case the greedy strategy of splitting at the first checkpoint that is available to the right is always correct, because checkpoint represents the letters that are allowed to be part of an ending character. So why wait till here, right? If you are given the choice to split the string, just split it here, then just split it here, just split it here. So if you are given the answer, then you can perform this split greedily. So this is a very interesting situation wherein the obvious greedy approach, when the answer is not known, does not work. But if the answer is known, the non-obvious greedy approach does work. So in the later slides, we will see how we can exploit this particular idea to come up with the intended solution. But even before that, note that we had assumed that someone would give us the optimal answer. But if no one is giving us the optimal answer, can we not try all the possible choices for ourselves and then assume each of one of them is the answer? Then perform the split greedily as we discussed and then see if the condition is violated. So the optimal choices, what are the possibilities for the optimal choice? So since there are C characters in the alphabet, so each character can independently be or not be in the final set. So there are 2 to the power C choices. So if you create a bitmask, and bitmask would represent which elements are part of the ending character, which elements are not part of the ending character. So if you create all the 2 to the power C bitmasks, then for each bitmask you create all of these checkpoints by coloring them. Then you apply the greedy strategy of splitting the parts, and after you have applied the greedy strategy, if any part has size more than k, you know that that particular choice of the bitmask was incorrect. So in this manner you can iterate over all the bitmasks and see which one gives you the smallest number of parts. So the time complexity for this would be 2 to the power c for iterating over all possible bitmasks, and O of n for verifying that there is no part with size greater than k. So this ends the first section of the video, wherein we were able to solve the problem D from the Codeforces round in n into 2 to the power c by deploying a greedy strategy but in a reverse fashion. Since we solved the problem in a reverse fashion, we already knew the location of all the possible checkpoints. Then we were trying to devise an algorithm to verify the correctness of this particular guessed bitmask. But if we really want to solve this problem in the forward direction, we have to come up with an algorithm that relies as little as possible on the unknown checkpoints, because we do not know their locations. In fact, that is exactly what the problem asks us to compute. But to do that, we can take inspiration from the previous algorithm. When will a particular bitmask be bad? It will be bad if the distance between consecutive checkpoints is greater than k. And why is that? Because remember that you had a greedy strategy of jumping from checkpoint to checkpoint. And if you deploy that greedy strategy, then the partition that you create over here will be of size 3. But since k is equal to 2, that constraints would be violated. So it is obvious that a bitmask will be good if the distance between consecutive checkpoints is less than or equal to k. But since we do not know the location of the checkpoints, we need to minimize the dependencies on the checkpoints keyword as much as possible. So if the distance between consecutive checkpoints is less than or equal to k, can you also say that the distance between an element and the next checkpoint will also be less than equal to k? This statement simply follows from the previous statement. So that implies that every sliding window of size k should have at least one checkpoint. We do not know where it should be located, but we do know that it has to contain at least one checkpoint. Just to verify this statement again, why is this statement necessary? It is necessary because if this particular window does not have any checkpoints, then even after applying your greedy strategy of jumping from checkpoint to checkpoint, the size of the partition that you will create will be more than k, because this size is k and this is k plus 1. So of course this condition is necessary. But why is this also sufficient? It is sufficient because if you have this element, and in this window if you have a checkpoint, suppose it is located over here, and naturally from this statement the distance to this checkpoint is less than or equal to k, so you can naturally jump to that checkpoint and no constraints would be violated. Then we know that the sliding window of size k starting from this element has a checkpoint, so we will jump to that element and then we will keep on performing that jump. So in fact this condition is necessary as well as sufficient. Now, you might think that how did even sliding windows of size k come into picture for this problem? And to most of the people, this is not something out of the blue. In fact, on my channel, I have two videos wherein a similar concept was applied. That is, whenever you see a constraints like k less than or equal to n, more often than not, it is helpful for you to investigate whether it has something to do with sliding windows of size k. So you can watch these videos called Optimizing DP with Sliding Window and Non-Palindromic Substrings, because we employed the same idea of sliding windows of size k in these problems. So now with that out of the way, we can say that we just need to come up with a bit mask such that each sliding window of size k contains at least one checkpoint, and that bit mask should contain the minimal number of set bits because we want to minimize the number of unique ending characters. Now let us consider the first window and assume that it has characters A, C and E. Of course, either A should be a checkpoint or C should be a checkpoint or E should be a checkpoint or a combination of them. However, this is a lot of words in English. Can we make this statement a bit more concise? To do that, initially we will mark all the elements as a checkpoints. So that is why we create a bit mask saying that A is a checkpoint, C is a checkpoint as well as E is a checkpoint. But that is not necessarily true because we just want at least one element to be the checkpoint. But how can you infer these three statements just by looking at this particular bit mask? So if this is the window bit mask and you might have the bit mask for the checkpoints in your guess, you can say that whatever the final bit mask that you come up with, it needs to preserve at least one set bit from this particular window mask. That is, if the set bit of C is preserved, it would indicate that C is allowed to be a checkpoint in that window. But if none of these set bits are preserved in the final mask, that would mean that this window has no checkpoints and our conditions would be violated. So since we are talking about preserving bits, let us recall the properties of bitwise AND. So the bitwise AND of 0 with any number is 0 and bitwise AND with 1 will preserve the bit if it is set. So naturally we need to think something along the lines of bitwise AND. And now you can see that if you take the bitwise AND of the window mask with the particular guessed mask for the answer, and if you do a bitwise AND of them, you will see that these 0 will be remaining 0, but these ones, they will be preserved only if the bitwise AND, only if the guessed mask has a 1 at this location. That would mean that this particular element is allowed to be a checkpoint. But if the bitwise AND is not preserving any of these set bits and these elements are already 0, so the bitwise AND would become equal to 0. That would indicate that the mask is bad. So we have the final mathematical expression now. That is, for every window mask, the bitwise AND of the window mask and the guessed mask for the answer should not be equal to 0 for it to be a good mask. Because if it is equal to 0, it means that the guessed mask is not preserving any of the set bits of that particular window mask, and when that happens, that implies that the window does not contain any checkpoint. So we have reduced the original problem down to a bitwise operation problem. That is, the simplified problem is, you are given a list of window masks. Specifically, there are n minus k window masks. You need to come up with a mask whose bitwise AND with each of the window mask is non-zero, and the number of set bits in the particular mask that you guess should be the minimum possible. Also, if you are watching this video to learn only about SOS DP, and if you don't care about solving the Codeforces problem, this is the place where you would start. So this is the reduced problem that we would be focusing on the rest of the video. That is, if you are given a list of integers representing window masks, and you need to come up with a mask that has a non-empty intersection via bitwise AND with each of the window mask such that the number of set bits is minimized. That is the problem that we are trying to solve. So an obvious solution is to iterate over all the mask from 0 to the entire full mask. Then for each of the guess, try to iterate over all the window mask, then take their bitwise and verify if it is 0 or not. If it is 0, it means that the guess was bad. So if it is 0 for at least one window, the guess was bad. So what is the time complexity of this solution? It is 2 to the power c into 2 to the power c, which is equal to 4 to the power c. Now let's look at the code for this problem. So for the code, we just implement what we discussed. So we add the first window, we create the bit mask for the first window by iterating over the elements, and if an element is present, we turn on the bit corresponding to that element in our bit mask. Then we keep sliding the window forward one by one. So if you want to slide the window, you need to remove this element and you need to add this particular element. So we find out the element that is being removed, which is at the location I minus k. We remove it from the window, and if all the occurrence of that element is gone, we unset that bit in the mask. Then we add the incoming element to the window and we turn on the bit corresponding to the incoming element. And after that, whatever mask that is remaining represents a window mask. So we indicate that the currently created mask is a window mask. Then at the end, recall that the string has to end at the final character. So whatever mask that you have, you need to keep this as a single window mask. So that is why we set it as true. Then to compute the actual answer, since you now have the locations of all the window masks, you can iterate your guess from 0 to full mask, and then you can go through each window mask, take their bitwise AND. If it is 0, you know that the guess was bad, and amongst all the good guesses, you count the one with the minimum number of set bits. So this solves our problem, but with time complexity 4 to the power c. This will naturally not pass the original Codeforces constraints, but you can submit this problem in my easy version in my Codeforces group. And this ends the second section of the video. Now we need to come up with a better algorithm to compute all the bad masks. And just to recall, a mask is bad if the window does not contain any checkpoint. And we have already discussed earlier that that can only happen when the bitwise AND of the guessed mask as well as the window mask does not preserve any of the set bits in window mask. That is, the bitwise AND should be equal to 0. So for example, if this is the bitwise representation of the window mask, then we know that the bad masks should not preserve this bit, nor this bit, nor this bit. So therefore you need to lock down all the 1 bits to 0. But what about the 0 bits? They can vary freely because 0 and any number is equal to 0. So you write these two conditions. So any mask that satisfies these two conditions, that is a bad mask. Now, what happens when I flip the bits of the window mask? And where did the intuition of this come from? Like, why are we suddenly thinking about flipping the bits of a window mask? We will come to that in a while. But let's see what happens to these two conditions when you flip the bits. So if you flip the bits, simply 1 will convert to 0 and 0 will convert to 1. For example, this gets converted to this. Here you can notice that since we added 0 over here, we will add 0 over here, and this bit was varying freely, so this bit will be varying freely. So the condition becomes that the 0 bits are locked down to 0 and the 1 bits can vary freely. So these two conditions, they look familiar to us. Why? Because these two conditions define what a submask is. And this is the exact definition of a submask. That is, 0 bits will always remain 0, but 1 bits can either remain 1 bit or it can turn to 0. So for this section, the understanding of what submask is a prerequisite. In this video, I will not dive into the details, but I already have a video on my channel that talks about what a submask is. The name of the video is Birthday Gift. You can take a look at it. But just to summarize, a submask is nothing but a subset of the set. So for example, this set has B and C, B and D. So any subset that contains either B or D or B and D, they will be a submask of it. But if you start adding A as well, like if you set this bit, it will no longer be a submask. So that is why 0 bits are always locked down to 0, because these were missing from the original set, but 1 bits can vary freely. So now our problem has turned into finding how many submasks are there for the flipped window mask, because that is exactly our answer. And now you can see the motivation for flipping the window mask. The motivation was that we can reduce it to a known expression, and the known expression is that we always allow the 1 bits to vary freely, but here 0 bits was varying freely. So not that it doesn't really change anything, but the only difference that it makes is that if you are in the realm of submasks, you will have a lot of online materials to reference and some reusable codes to use, because the theory of submasks is well studied on the internet. So you can take reference from that. So it doesn't mean that you couldn't solve the problem without flipping the window mask. It just means that after flipping the window mask, it gets converted into something familiar, something that you are already aware of, and something that other people are already aware of, and you can use their code to solve the problem. So to summarize, all the bad masks for a given window is nothing but the submask of the flipped mask. So if we can flip this window mask, and then if we can find all the submask of this mask and mark it as bad, then we should be done. So now we need an algorithm that can iterate over all the submasks of a given number. And that is also a standard problem. You can find the idea for that problem in the USACO guide, and I will add a link to that in the YouTube comments as well. And the time complexity for that is 3 to the power C if you iterate over the submasks efficiently. So let's go over the code. So in the code, we will iterate over all the window masks, and for each window mask, we will flip all the bits, and then we use the standard algorithm for iterating over all the submasks efficiently. So this code is copied from the USACO guide. You can take a look at it there. So the time complexity of this is 3 to the power c. And in fact, this is enough to solve this problem. So if you submit this code on Codeforces for the problem for which the editorial you were looking for, it should pass. And that is it for the problem. And this ends this section. But if you really want to learn about SOS DP and how this time complexity can be improved from 3 to the power c to just c into 2 to the power c, you can watch the next section as well. In this section, the problem that we are trying to solve is how to iterate over all the submasks of a given number and mark those submasks as bad. For example, this is a bad mask and that is why it is colored in red. We need to mark all its submasks as bad as well. To do that, we will systematically generate all the submasks. Recall that a submask is a number where the 0 bits are locked down, but the 1 bits can vary freely. So we can either turn off the first 1 bit or the second 1 bit or the third 1 bit. Similarly, we can do the same process again. We can turn off the first 1 bit or the second 1 bit. Then we repeat this operation for all the nodes that we have. Now, take a moment and convince yourself that the tree that is created by this recursive process, it will contain all the submasks that is possible for this root. And in fact, you can say a stronger statement, that is, for any node, all the nodes in its subtree will be all the submask that this mask has. So it is true for this root node, but it is also true for this node. That is, all the submasks for this node will exist in this subtree. Now, notice some observations about this tree. It can have a maximum of C levels. Why? Because in each level we are removing one set bit. So there can be a maximum of C different levels. Another observation about this tree is that each node in the same level will have the same number of set bits. For example, this is level 0. It will have 3 set bits. This is level 1. It will have 2 set bits. This will have 1 set bit. And you can see why this statement is true. This is because when we were creating a tree, when we went down a level, we set off exactly 1 bit. So that is why if the number of set bits in this level is b, in this level it has to be b minus 1. So to summarize, if you create a submask tree, so this is the submask tree for this number, some observation are that for any node, all the submasks would be present in its subtree. That is one observation. Second observation is that there can be a maximum of C levels, and the third observation is that in each level all the nodes will have the same number of built-in pop count, that is the number of set bits. Let us consider another example of a submask tree. This is a bad mask and that is why it is colored in red. If it has 4 set bits, the next level will only have 3 set bits. The next level will only have 2 set bits. Now let us consider one node. Suppose it is this node 0011. Since this node is a submask of this node, then we will go to this node and we will color it as red. But since these elements are also submasks of this mask, we will color this as red, this as red as well. But what happens when in future you discover that this is also a new bad mask? So you will try to iterate over its entire subtree, that is you will try to iterate over all the submasks of this mask and color it as red. But since the parent for this node has already been processed, that means its entire subtree is already colored in red. So why do you want to go over all the elements again and color it as red again? So here you can notice overlapping problems. That is, when you are processing an element and when you are going into its subtree to color them as red, you do not need to do that operation if its parent has already been processed, because you would just be doing repetitive work. And now you can see the connection between this and Fibonacci numbers. So if you recall the basic recursion tree of Fibonacci numbers, it forms kind of the same tree where you say that you will not do the work of going downwards in the tree again and again. Instead, you will save whatever result you computed in this node only so that you can reuse it. But here the concept is that instead of going down to the subtree and coloring the red nodes in red again, you see if the parent has been processed. But another way to look at it is that if this is the parent, right, why does it have to go into the entire tree to process and color all the nodes in red? So think of it as a tree. Think of it as a tree DP problem. If I ask you to color all the nodes in red, will you write the code to go into each node and color each node in red? Or will you be smart about it and you will say that, okay, if you want to color every node in the subtree as red, I will apply a trick and I will say that I will only color the next level as red. I will only color this level as red, and then I will recursively call the coloring function for each of these children, because that does the job as well. So the parent is not really iterating the entire subtree at the moment. It is just pushing this responsibility to the children. This brings us to the most important part of the video, that is, how does SOS DP works behind the scenes. And keep in mind that we haven't yet discussed what SOS DP is, but we will do that in this slide and the next slide. If in future you forget everything except one thing about SOS DP, I want you to remember this statement, that is, subsets of a subset are a subset of the original set. Before we dive into this inception, let us break down this statement. So this is the set, this is the subset, and this is the subset of a subset. So this is level 0. Level 0 is a set, level 1 is a subset, and level 2 is a subset of a subset. So this statement says that the subsets of a subset, that is all the elements that are in level 3 and below, they are a subset of the original set. So here you can use subset and submask interchangeably. So this means that all the elements that are in level 3 and downwards, they are also the submask of the root. And it is actually pretty intuitive to see, because we were creating the submask tree of the root. So this particular element is a submask of this element as well as the root. So that is why subsets of a subset. So subsets of a subset, so this, which is this element, they are also a subset of the original set. So this means that if you want to iterate over all the subsets of a given mask, or if you want to iterate over all the submasks of a given mask, you don't really need to iterate over all the submasks at once. what you can do is just iterate through the level 1 submasks, that is all the submasks where only one bit was altered, and you color them as red. You color them as red because why do you not need to iterate over all of these subsets or submasks? It is because sooner or later you will eventually reach this node, and when you do, you can start coloring the next level because you will apply that same algorithm recursively. So you can offload the responsibility of coloring the entire subtree to just the next level. So if this is at level L, it will offload the responsibility of coloring the entire subtree to level L plus 1. And this is what SOS DP is. So the full form of SOS DP is sum over subsets DP. That is, if you want an efficient way to iterate over all the submasks of a given mask, the only thing that you need to do is iterate over the level 1 submasks, that is all the submasks where only a single bit differs. So you iterate over only the level 1 submasks, you color them as red, and you assign them the responsibility of coloring their entire subtree as red whenever their time comes. So using this idea, that is subsets of a subset are a subset of the original set, you can clearly see that previously the amount of operations that we were doing for each node, it was 2 to the power set bit count, which could be 2 to the power c, right? Because we were iterating through all the nodes and we were coloring them in red, and that led to duplication. Why duplication? Because this node was being colored red multiple times, one through this and second through this. But if we start offloading the responsibility to only the next level, then in each node the amount of work that we will need to do is equal to the number of set bits in this node, which is equal to a maximum of c. So every node will do a maximum of c work, and the total time complexity would be 2 to the power c into c. But for that to work, you need to remember that this process needs to be done in a specific order. And what order is that? We'll talk about that in a while. For the code, first we iterate through all the existing window masks, we flip it, and we say that the flipped mask is bad. And keep in mind that this flipped window mask represents the root of the submask tree. Then we need to do a level order traversal, that is, we need to iterate nodes in their BFS order of decreasing set bits. So you do a decreasing set bits iteration, and then you start processing all the nodes in that level. So their order does not matter because they are in the same level and they are not connected to each other. Then you need to check if this particular element is colored as red or not. If it is, then you need to iterate over all the child and offload the responsibility to the child. That is, you tell the child that you need to color your subtree as red. So that is why you iterate over each of these child. And how do you know it is a child? You see if the ith bit is set. If it is set, it means that you have an opportunity to create a child with exactly b minus 1 bits. So that is why you create a child by unsetting that bit over here, and then you mark the child as red. So you don't really iterate over the entire subtree, instead you only iterate over the child. So you mark the child as red, and then sooner or later you will arrive at the child, because if you are processing this node currently, by the time you finish the level order traversal of this node, you will reach this level, and when you reach this level, you will see that okay, this child is colored as red, let us mark the subsequent child as red as well. So in this manner you will see that each node will be colored in red exactly once. and that is how we prevent overlapping subproblems. That is, instead of iterating the entire subtree and coloring it as red, we will say that the children's subtree, all the children would be covered as red, and since the subsets of a subset are a subset of the original set, we will offload the responsibility to these children. Now the time complexity of this might look like c square into 2 to the power c, because there is c over here, there is c over here, and there is 2 to the power c over here. So it might seem like c square into 2 to the power c, but it is actually c into 2 to the power c. And the reasoning for that is quite simple. Take any node. How much work are you doing for that particular node? So if that node can have a maximum of c set bits, you are only doing O of c amount of work for that node. And since you are visiting each node exactly once in their BFS order, the total amount of work that you are doing is c into 2 to the power c. And in fact, this is the same idea, that is traversing these nodes in their BFS order of decreasing order of set bits count. This is the same idea that we use in the traveling salesman problem as well, to propagate the information to lower levels. Now if you look at the editorial, if you look at the official editorial, it in fact says that the problem can be solved via simple DP. It doesn't even mention the concept of SOS DP, and that is kind of true as well, because by the time you gain expertise in bitwise operation, right, you might not even realize that you are using SOS DP behind the scenes. Okay, so in the next section we will talk about a fancy optimizations that the editorial has done, where the code looks pretty simple and innocent, but behind the scene it is using the same concept of SOS DP that we have discussed in this video. And the concept is that the subsets of a subset are the subset of the original set. So if you process nodes in some specific order, you can keep on offloading the responsibility to the lower levels. While implementing the traveling salesman problem, and even while implementing this problem, my preferred approach is to have two for loops. The first for loop will iterate over the decreasing set bits, and the second for loop will iterate over all the masks in that particular level. This idea seems very intuitive to me, because the BFS order one can visualize that the contribution is flowing upwards from the tree to downward levels. But one thing that has always bothered me is that some people are able to get away with just one single for loop by iterating over all the masks in either low to high order or high to low order without any consideration of the set bit count. And their code is actually correct and it works. So it has bothered me for a long time, like, why does it work when you are not following any order of propagating the information in the tree? So one day I asked Aryan in his Discord server, and he explained the idea to me. So this section is a bit advanced. So the idea is that instead of iterating over all the set bits in decreasing order and then doing a level order traversal, you can instead simply iterate over all the bit masks from higher order to lower order and do the contribution technique, that is, push the responsibility to the children, and that will still work. But why does it work? So it works because, let's look at the last slide again. It will work because this node, it will take contribution from its parent, and previously we derived that the parent will have a higher set bit count, and that is why we deduced that we need to iterate in decreasing order of set bits. But let's do another observation. So this node will certainly take contribution from a higher set bit count, that is true, but another observation is that it will only take contribution from its supermask. And what is an important property of supermask? So a supermask is always greater than a mask. So that means since it will only take contribution from supermasks, so if you were to process all the elements in decreasing order, by the time you reach a single element, you will have processed all the parents that are possible, because all the parents are the supermask of this mask. So you don't really need to maintain that BFS order anymore, because the iteration order from high to low will guarantee that by the time you reach an element, all its supermask, that is all its parent, has been processed and none of its child has been processed, because the child is a submask, right? And submask are less than mask. So that means that none of the child has been processed and all the parents have been processed, which is exactly what we want. So so that is also a very cool trick, okay, that works, wherein you can simply iterate from high to low, and you can assume that by the time you reach a mask, all its parent have been processed and none of its children has been processed. So I encountered this idea while solving these two problems. So one is shuffling songs on Codeforces and one is compressed strings on at Coder. I will link these two problems in the YouTube comments as well. You can attempt it. So if you look at the code, we take the same code as before, where we were iterating over the pop count in decreasing order, but now we will simply iterate over all the masks in decreasing order, and then we will iterate over all the children, and then we will color the children as red because we want to offload the responsibility. And this is the code that you might see in most of the submissions, that is write most people write TSP DP in this style, but the time complexity of this as well as the built-in pop count approach is same. So it's up to you which one seems more intuitive to me. So for example, me particularly, I like the set bit count approach because that looks more intuitive to me, but I hope over time I will also get accustomed to this as well. Like even now I'm clear like why this works, but if I take like 3 to 6 months break from competitive programming and I come back, I might find it hard to reason the proof of correctness for this. But for the BFS order, it is apparent to me why that is happening. So this is the simple code that works for this problem, and the time complexity is c into 2 to the power c. Now you can see that the editorial has this code, and the editorial claims that um, finding all the submasks can be done with simple bitmasking DP. But behind the scenes, it's not really simple, because the hidden idea is the main property of the SOS DP, that is submasks of a submask are a submask of the original masks, right? So that is why you are able to write this loop. So just 3 to 4 lines of code doesn't mean that the understanding was easy, but yeah, I hope that this problem can act as your template problem for understanding SOS DP in case you forget it in future. And the reason why I created this video is that you can have one problem where you can submit multiple approaches so that you fully understand what is a mask, what is a flipped mask, what is a submask, etc. One thing that I would like to remind you again is that a node can have multiple parents in this submask tree. However, in this problem, even if you end up coloring a node multiple times in red, it is okay. However, this might not be the case in other problems. For example, consider the classic problem of SOS DP, that is, you need to compute the sum of values of all the submasks. Now, in this formulation, if you recursively add the answers from this subtree, this subtree, and this subtree, you will end up over counting, right? Because you will end up over counting this and this. And if you try to take the approach where you directly iterate the submasks or you directly iterate the masks in the natural order as we discussed in the last slide, that might also lead to overcounting. So for example, this is one approach where you iterate the masks in increasing order, because you will query for the submask and then you will add it to that mask, right? But this code doesn't work because it will have duplicates, and you can see why. However, if you swap the order of these two loops, right, if you add the I loop as first and the mask loop as second, this code starts working. So my question to you is, why do you think that happens? Like, how does swapping the order of for loops remove the duplicate counting problem in submasks? That is a topic for another video, but let me know your uh, answers in the comment section below. I have added all the slides, code, easy version, practice problems, and the similar videos in the pinned YouTube comments. You can check it out. And all the code that we have discussed in this video will be available on cfstep.com.